Hello, my name is Amos Peter, and you're welcome to these lectures on the series of circuit theory. In this lesson, we'll consider the phase angle introduced between an alternating voltage and current when the circuit contains only pure ohmic resistances. Now, let's assume you have an electrical circuit with a voltage source, which is sinusoidal in nature, and that very particular circuit is only connected to just a single pure ohmic resistance, and then the circuit will have a current of I flowing through. Now, assuming that the voltage applied to the circuit is of the form V is equals to Vm sine theta, which is the same thing as Vm sine omega t. Let's call this equation 1. Now let R be the ohmic resistance, and small I also be the instantaneous current flowing through the circuit. Now, for balance and in accordance to Ohm's law, it is expected that the voltage V, voltage drop through this very particular resistance, is going to be of the form of V is equals to IR. Let's call this equation 2, and this is equation 1. Now, substituting Vm sine omega t for the left hand side of V on the second equation gives us Vm sine omega t is equals to IR. Now, making I the subject of the formula in this equation gives us that I is going to be equals to Vm all over R sine omega t. Let's call this our equation 3. Now, if you look at this equation 3, this is also an equation that is in a sinusoidal form. And of course, we all know that for any sinusoidal signal or voltage, it is of this form, which follows after the sine wave. Now, it could be seen from here that this very particular current, assuming this is the current I in the form of a sinusoid, that this very particular current I can only be maximum, that is Im, when sine omega t is equals to unity, which is 1. In other words, when the phase angle is at 90 degrees or pi all over 2 radians. That's the only time that the current here can be maximum. So this implies that Im current is maximum is going to be equals to Vm all over R when sine omega t is equals to unity, i.e., just like I said, when omega t is equals to 90 degrees or pi over 2 radians. Now let's call this equation our fourth equation. Now, substituting Im, this Im for Vm all over R in the third equation gives us I is equals to Im sine omega t. So let's call this our fifth equation. Now, a careful comparison between this last equation, equation 5 for current, and our first equation for voltage, you will see that both equations are of the same form. The only difference is that while the first equation describes the voltage, the second equation describes the current. So this means that both the voltage and the current in this very circuit that is composed of only pure resistance are in phase with one another. And what do we mean when we say a circuit or two parameters signals are of the same phase? It simply means, supposing we have our XY plane, and if this is the voltage, which is in the sinusoidal form, if this is V is equals to Vm sine omega t, then it is expected that the current will also be of a similar shape, where this is I is equals to Im sine omega t. It then means that both the voltage and the current rises and falls at the same time. For example, when the voltage is at location 0, the current is also at 0. By the time the voltage is maximum, the current is also maximum. By the time the signals makes a reversal, it's still the same thing on the negative axis. By the time the voltage is 0, the current is 0. By the time the voltage is -1 or negative maximum, the current is also maximum on the negative side. So it then means in a purely ohmic resistive circuit with an AC voltage applied to it, we say both the current and the voltage are in phase with one another, as can be seen from the current equation that was derived from the given circuit parameters. Now, this very particular relationship can also be represented vectorially in this form. So assuming this is our voltage, where the length of this arrow signifies the magnitude of the voltage, then it is expected that the current will also lie along the same plane together with the voltage. So that is that about AC current passing, or voltage rather, passing through a pure ohmic resistance or resistor, and we've been able to show that both the current and the voltage are in phase with one another. So I would like to hold on at this point, and thank you for viewing. I will also encourage you to look for my subsequent video on AC current through a pure capacitor and AC current through a pure inductor. Thank you very much for listening. See you next time.